4.2, more logarithms. I know you're excited. So, if you remember back in the previous sections, we were working with exponents and our exponentials. And I took that day in class to kind of break out for you if you have 2 cubed times 2 squared, that is the same as 2 to the 3 plus 2. By showing you that 2 cubed is 8 and 2 squared is 4, so 8 times 4 is 32, which if I return back to a 2 to the something, that's 2 to the 5th, which is the same as 3 plus 2. Now, the 2 cubed quantity squared, right, in this case, because I'm raising it to a power and then raising it to a power again, I end up with a multiple of 3 times 2. And so in that case, right, 2 cubed was 8, 8 squared is 64, and then that's the same as 2 to the 6th, or 3 times 2. So I did that in class. Similarly, you can talk about this for division, right? 2 cubed divided by 2 squared would be an 8 over a 4, or a 2, which is the same as the difference in the two values, 3 minus 2, in order to get that 2 to the 1. And we also talked about how we define roots, right? So in here we have a square root of 2 cubed, which is the same as 2 cubed raised to the 1/2 power. And then we can use that multiple, 3 times 1/2, to get us a power of 2 to the 3/2. Okay, so I'm going to use this to define our laws for our logarithms, because the logarithms are directly defined through exponentials, so we can then use this kind of relationship with our exponentials to define a relationship between our logarithms. So if I try to take log base 2 of 2 cubed times 2 squared, that was the same as log base 2 of 2 to the 3 plus 2, right? And we talked about in the last section how this 2 to the and the log base 2 cancel each other and leave me with just the 3 plus 2 that's in the exponent. And so you can generalize this a bit by I will generalize it later, but anything that you're multiplying ends up getting you addition at the end of the day with a logarithm, because a multiple of two exponentials adds the exponents if they have the same base. And so you end up with the same format in logarithms of the multiplication becoming this addition. Now, if I take a look at the other one that we talked about, 2 cubed quantity squared, right, then that's the same as log base 2 of 2 to the 3 times 2. So then again, those two things cancel each other, right? And I'm left with 3 times 2. And so this extends with any kind of exponent becomes a multiple when you take a logarithm. This extends again, right? Division behaves much like multiplication did up here. We end up with a 3 minus 2 instead of 3 plus 2. And so you end up with subtraction, or the difference between those exponents in your logarithm result over here. So, and it's for the same reason. This cancels with this, and I'm left just with my exponent. For the roots, if I take a square root of 2 cubed, then we simplified that to 2 to the 3/2. So this is the same as log base 2 of 2 to the 3/2, which, because those cancel, again, will get me 3 divided by 2. Now, so anytime that you're taking a root, you end up with division. Or anytime that you end up taking it to some power, that's multiplication. And remember that multiplication and division are very, very related. If I'm multiplying by a fraction, it's going to have a similar behavior to dividing by whatever the denominator is in that fraction, right? And then you just have to be careful, because multiplication inside equals plus outside. Division inside equals subtraction outside. So these are things to get comfortable with. I did numbers here. I'm going to generalize it so you have effectively formulas to work with, to refer to, because it does generalize very well. If I have a multiple of sum a to the x times a to the y, and I take a log base a of that particular setup, then because they have the same base, the exponent in this case becomes the x plus y, right? And log base a cancels out my a exponential term, and it leaves me with just my exponent, x plus y. To generalize this, I can treat a to the x and a to the y as some constant value, because if I took 2 to the 3, I'd get just some constant 8 out, right? And that's where this idea is coming from. So if I set a equal to a to the x and b equal to a to the y, so I'm no longer considering what the base is, but there is some value x where a to the x is equal to a, and some value y where a to the y is equal to b. So I can use the same concept from the line above to determine what log base a of a plus or a times b is. So if I have this, I can use the same concept, right? If log base a of a to the x plus y, which is the same as log base a of a times b, was x plus y, well, x, if I represent it in terms of the logarithm, is log base little a of big A, right? That would get me x, and log base a of b would get me y. And so my x plus y can be represented through the actual value of a to the x and a to the y as any time that I take a anytime I take a logarithm of a times b, that's the same as that same logarithm of a plus that logarithm of b. So this is the general version of the concept that extends from the fact that that multiplication becomes addition. So when we take this logarithm, the multiplication inside becomes addition outside. We can also do this for exponents. So remember, right, a to the x raised to the y gets me an a to the x times y, and if I take a log base a of a to the x times y, then again, these cancel each other out, leaving me with just the exponent x times y. And so in this case, an exponent becomes a multiple. So if I set big A equal to a to the x again, so I use the same thing we used for the last one, and then b, little b, is then equal to y, then any time that that constant is raised to another power b, that is the same as multiplying that logarithm of a by its exponent b. So any exponent can be effectively pulled in front as a multiple of the logarithm of its base. Okay? If we extend the same concepts with division that we had for multiplication, right, a times b, remember that a to the x over a to the y is the same as a to the x minus y, which gets us, again, when our bases cancel here, the logarithm and the base a, I just get my exponent, which is my x minus y. So division translates to subtraction, which gets me, again, if I make the same assumption that I made for the multiplication, my big A and my big B, my log base little a of a over b becomes subtraction outside. Okay? So this is the generalization. We just did this with numbers, then we did it with a to the x's, and now I'm showing it to you in the general form that it is in the textbook. Roots, same thing, right? That's division in your exponents instead of multiplication in your exponents. So if I have the yth root of a to the x, that's a to the x over y. And because I'm taking a log base a of an a to a power, I just get back my exponent, x over y. Now, if I use the same thing that we used for raising an exponential to a power, right, a equals a to the x and little b is equal to y, then the bth root of a would be a 1 over b multiplied out in front. Again, the bth root corresponds to a power of 1 over b, and so that exponent effectively comes in front as a multiplicative constant to the rest of the problem. And that's true even if I had log base 2 of 4 to the x, that becomes x times log base 2 of 4. It doesn't, whatever is in the exponent, whether it is a constant or it is a variable, it still can be pulled out in front as a multiplicative constant. Okay, so let's use these laws in order to simplify and solve equations that involve logarithms, because that's what you want to do. You want to simplify and solve equations that happen to have logarithms in them. And these are all tools to help you do that in a very efficient way and make the problem nicer. So if you're ever questioning how they work, you can always just test some of the numbers on your calculator. Check it. What do you think happens? Verify that that is what happens. And using a combination of 2s and 3s is usually a good way to do that because they're small numbers, so you know that it's consistent. As an example, just to if you are trying to say evaluate log base 2 of 32, and you know that 32 is 4 times 8, you could then go, okay, so I know that log base 2 of 4 times 8 is the same as log base 2 of 32. So I could plug log base 2 of 32 into your calculator. If you have base b, we'll get there. Later I'll show you the change of base formula, so you can actually do it for any base of a logarithm. But if I want to check, if I have multiples inside, right, I have 4 times 8, so how is this going to be related? And from above, we talked about multiplication becoming addition outside. So log base 2 of 4 times 8 becomes log base 2 of 4 plus log base 2 of 8. Okay, and you can verify that by substituting either of those into your calculator, or if you know them, right, 4 is 2 squared and 8 is 2 cubed, so you end up with the 2 coming down in front, and log base 2 of 2 is 1. The 3 comes out in front. Log base 2 of 2 is 1, so you end up with a 2 plus a 3, getting you 5. And 2 to the 5th is our 32 that we had before. So it's consistent. You can just check these things with numbers if you're unsure of whether it's going to work. Plug something in. It's a great way to go about checking your answer. There's 2 ways that we'll use these. One is to combine logarithms, so taking something that's spread out, like log base 2 of 4 plus log base 2 of 8, which is just what we were talking about, so it's a good reference point, and then combining it to get your log base 2 of 32, and then the other one that we'll do after is expanding it out, where it is more like what we just did, where you take the log base 2 of 32 and you expand it back to a bigger set like we have here. And specifically, in this particular case, you would get it all the way down effectively, because these are, 4 is 2 squared and 8 is 2 cubed, so you can simplify that all the way to 5. But more generally, you're just trying to write multiple logarithms out. You're just trying to expand it to a bigger form, so it's simpler in terms of each piece being simpler. Well, let's look at another example. So if I have log base 3 of 9 minus log base 3 of 27, then subtraction corresponds with division when we simplify. So that becomes a log base 3, since they have the same base, 3, of 9 over 27, which you can reduce that fraction to a log base 3 of 1 over 3, which, what is log base 3 of 1 over 3? That's 3 to the negative 1, so it corresponds to our exponent of negative 1. Another example is using the roots. So if I gave you 1/2 log base 4 of 16, that is the same. I can take this, since it's a multiplicative constant out in front, and I can convert it to an exponent, just like we did the other direction, taking an exponent and converting it to a multiplicative constant. Now that 1/2 becomes the power for the 16, which means that it's the square root of 16. So log base 4 of the square root of 16, the square root of 16 is 4, so it's log base 4 of 4. And if we have the value that's the same as the base, then we get out 1, right, for logarithms, because 4 to the 1 is effectively what we have. Functions of x get a little bit weirder. So I'm using constants in all of these examples here to just demonstrate what you're doing, but ultimately you want to do this with functions of x. So you want to have, say, log base 2 of x minus 4 minus log base 2 of 3. and be able to take the fact that there's a minus here and convert it to this division that we see inside of our logarithm. So log base 2 of x minus 4 minus log base 2 of 3 is the same as log base 2 of x minus 4 divided by 3. This is combining the logarithms. And this is, hopefully you'll get more practice with this over time, but that's ultimately where you want to go with it, our functions. The other direction is expanding them out. So if I give you log base 2 of 4 times x, how do you then convert that to logarithms that are smaller individually? So multiplication, we convert to addition. So I have a log base 2 of 4 plus a log base 2 of x. I can obviously simplify this log base 2 of 4, but there's nothing I can do with this log base 2 of x to simplify further into smaller components. Log base 3 of 3 divided by x, well, that's log base 3 of 3 minus log base 3 of x, or 1 minus log base 3 of x. Log base 4, 9 times x, you have log base 4 of 9 plus log base 4 of x. And since we know that 9 is 3 squared, we can use the exponent, right, log base 4 of 3 squared plus log base 4 of x, and move that exponent out in front to get us to log base 4 of 3 plus log base 4 of x. So you're looking for any components that resemble these laws. Then you just want to apply those to simplify what you have. So for example, right, 2 squared is 4, and so we can simplify the log base 2 of 4 to a 2. We can simplify the log base 3 of 3 to a 1, because 3 to the 1 is 3. And then here we can move that 2 out in front to get our form 2 log base 4 of 3. What I don't want is, I don't want the decimal value of 2 log base 4 of 3. I want the form that simplifies the logarithm. So you want to simplify the logarithm down as much as possible, but if it's not an integer, if it's not 1, 2, 3, 4, and so forth, if there's any decimals involved, don't give me the decimal, give me the logarithm. That's what we really want to see. We want to see you reduce the logarithms down. If you want to evaluate them, I mentioned before the change of base formula that you can use to then evaluate any logarithm. It's because we don't have log base b in all of our calculators. So you can't necessarily plug in log base 2 of 8 to verify that that's 3 if you have one of those calculators. So the change of base formula is what allows you to then evaluate this without needing log base b built into your calculator. Specifically, all we need is the ratio of some other logarithm evaluated at x over that same logarithm evaluated at the base. So log base b of x is going to be given by some log base a evaluated at x also, but then divided by log base a evaluated at b. So for your built-in log for log base 10, that would just be log x over log b. So if I want to verify, that log base 2 of 32 is 5, all I need to do is take log of 32 and log of 2, and then take that log 32 over log 2, and I should have 5. Verify it. Log base 2 of 5, that I don't have an integer value for, but all you need to do is then take log of 5 and log of 2. Log of 5 over log 2 gets you about 2.32193. So 2 squared is 4, and 2 cubed is 8. 5 is a lot closer to 4 than it is to 8, so this kind of makes sense, right? And then for log base 3 of 7, perhaps, you would have log of 7 over log of 3. That reduces to about 1.77124. Now, 3 to the 1 is 3, and 3 squared is 9. 7 is a little bit less than 9, so that makes sense. 1.77 is a little bit less than 2. And then finally, another one, log base 4 of 8. Log of 8 over log of 4 gets you 1.5. Okay, well, 4 to the 1 is 4, and 4 squared is 16. And so this kind of makes sense. And actually, if you think about it, the square root of 4 is 2, right? And this 8 is 4 times 2. So that's 4 to the 1 times 4 to the 1/2. 1 plus 1/2. 1.5. Pretty cool. If you're wondering why does this work, which I think is a good question to ask, Let's use this idea, log base 4 of 8 equals y, for a second, just so I can show you, right? So what we're saying is that if log base 4 of 8 equals y, then that is also saying that 4 to the y is then equal to 8. When we're trying to figure out what that value is. If you take the logarithm of both sides, then you're taking the logarithm of 4 to the y and the logarithm of 8. Now, y is an exponent, so we can move it in front, and we have y times log of 4 equal to log of 8. Huh, okay. And that's okay because we took the log of both sides, so we're consistent. And then you have y times log of 4 is equal to log of 8. Then all you need to do is divide both sides by log 4. And you get your change of base formula right out of it, right? Log of 8 over log of 4. That's exactly what we just did to get the 1.5. So you get the same results as you would if you were to actually be able to evaluate log base 4 of 8. But this opens it up so you can evaluate any logarithm. Try graphing them. Let me know how it works out. Come in with questions. See you then.